Okay, now. Very much in, let's get the thanks semester over with mode. So, this week it's public coordinates and then, next Monday is conic sections as the last new material. And then next Wednesday is, review. The practice, final exam and solution are posted in Canvas on the, main page. It will not have any conic sections material. I just realized on my other site, I forgot to put it there, but at least it's available to everyone, but it will be posted soon too. So there are 20 problems in total, for a 2.5 hour duration regular final exam. There will be a formula sheet. So when you download the practice file itself, you'll be able to see what the formula sheet is, so you know you don't have to spend time trying to memorize those things.
Right.
All right. Okay.
When is it?
Let's see. It's on Monday, May 8th, 10:45 to, yeah, so. For 2 weeks from today. Okay. Right. So it'll be one last time to have everyone here in the room. I shouldn't have to say this, but please show up on time. Plan earlier, just get going earlier. It drives us when someone shows up significantly late. It's like, okay, it's tossing away points. Okay. Yes.
Oh, and the final will only cover everything that we have taken since the last test, right?
Yeah, so,
All the
so
vectors.
in the notes, it's section 2.1, which is on like three-dimensional coordinate systems vectors. So what is a vector? All the way through 3.4, which is what I'm covering this week. Okay.
So all the parametric, so everything from vectors, parametric stuff.
Yes. Yeah, so starts here, ends here, everything in between. Yeah.
Also, parametric stuff is a technical term.
Well, yeah, very. Okay, so be sure to take a look at the practice finals and, see if you know how to do those. If you're in trouble with them, if solutions not enough help, we can certainly talk about them during the, review. Okay. Now. And as a reminder, for homework. Lowest homework will be dropped. So for example, the 13th homework is one that's on conic sections. That is, not gonna be in the final anyway, so for instance, you might decide to make it that one. Or if you have a particularly low grade, then you can go ahead and do it and have that other one dropped. So, up to you. All right. Fine. Now I'm going to. polar coordinates. Okay, now, these have come up a time or two before. But now they'll be the main focus. Okay. So what you're accustomed to, Cartesian coordinates, point in the XY plane, identified by values coordinates X and Y, where X is the distance from the origin to the point along the X-axis, and then Y is the distance from the origin to the point along the Y-axis. Okay. By contrast, polar coordinates, we're still working in the same XY plane, but we're identifying points differently. These values are the coordinates R and theta. So R is the distance from the origin to the point. So using the distance formula. And then theta is the angle that this segment between the origin and your point makes with the positive x-axis. So this leads to what's called a polar rectangle. If I consider x values and y values that are both between two fixed values, like an interval in x along with an interval in y, that would define a rectangle. A polar rectangle is defined in a similar way, but it's definitely not a rectangle. But as an example, suppose I choose all points of R values between 2 and 3, and theta values between, I'll make up two angles here, 5 pi over 3 and 7 pi over 3. Okay. Okay. Then, so that would consist of all points that have a distance. Whoops, that's a double circle. Of the origin, distance from the origin between 2 and 3. So points within this ring here, except not all angles. Angles that are between 5 pi over 3, which is this angle here. And then 7 pi over 3, it takes me past 2 pi up to this point. So all points between these two angles, but also between these two distances. So I'm going to shade in the region. So this is my polar so-called rectangle. That's pretty badly drawn.
It works.
Yeah, so. Okay. Now, so what I'm going to show you today is first converting back and forth. Given a point in either coordinate system, how to get to the other. And then we'll look at the polar equations and tangents. Okay, so first, if we have polar coordinate of a point, and we want the Cartesian coordinate, that's the easier direction. So you're given R and theta, and you want X and Y. Well, if we go back to this picture here, by right triangle trigonometry, this vertical distance right here, this is R sine theta, and this distance right here is our cosine theta, so using opposite over hypotenuse and adjacent over hypotenuse. So that's how we convert from polar to Cartesian. But because of the periodicity of cosine and sine, they're both 2 pi periodic. That means that points do not have a unique representation. Also, I've always find R to be a distance then from the origin to your point, and therefore should be non-negative. You could conceivably use a negative R value. It's just how do I interpret it? So if this is my angle theta, then this is a point R theta, and I could go the other way along this same line. So this would be a point minus R theta. Okay. So that's something to be aware of when it comes to, especially when it comes to graphing polar equations. But I could also represent this same point using a positive R value and a different angle. So here's an example. So I'm going to give 3 R theta pairs. Here's polar, Cartesian. We'll start here, R theta. And over here we'll have X, Y. So we'll have R equal to, first case, 1, and then pi over 4. And then the next one will have minus 1, 5 pi over 4, then 1, 9 pi over 4. So, so for first one, R is 1 and theta is pi over 4. So what are my X values, X and Y values going to be?
Square root of 2 over 2 for both.
Yeah. Because it's getting cosine and sine of pi over 4. Okay. So now for the next case, we have R being -1. Then we have a different angle, 5 pi over 4. So if you mind where cosine is positive or negative. Well, cosine of 5 pi over 4 is minus square root of 2 over 2.
Yeah, times -1.
Yeah. So we have minus square root of 2 over 2. That's square root of 2 over 2. And what about the sine?
All the, so. Negative.
It'll be negative because, yeah, because we're in the lower half of the circle now. Yeah, you were thinking of 3 pi over 4. Yeah, okay, yes. Okay. Someone said the answer, but okay. So sine will be negative. So here also we have minus of minus square root 2 over 2. So same point. What's a really quick way to do the last one? Subtract 2 pi, which brings you back to this angle. You're subtracting 8 pi over 4. So in other words, I described the same point, the XY plane, in 3 different ways. Just to highlight the non-uniqueness that any point in the XY plane, so XY coordinates, those are unique, but they can be represented using infinitely many combinations of R and theta values. Another example of non-uniqueness, suppose you're at the origin. Well, actually, that's the non-uniqueness going every way. Dang it. Alright. Now. Of the origin, let R equal to 0. On any theta whatsoever. Okay. Now, going the opposite direction. So if you're given XY. And you want R and theta. So the equations. Involved are R is square root of X squared plus Y squared. And you could try to find negative R value, but we'll just keep things simple and go for non-negative one. And then using right triangle trigonometry again, the tangent of theta is opposite over adjacent, which is Y over X. Now, this came up once before, that does not mean you just go directly to theta is inverse tangent of Y over X. That does work in some cases, but not all. So getting R is straightforward, but theta is equal to, it depends. It is equal to inverse tangent of Y over X if X is positive. Because, and the reason for that is inverse tangent, the way it's defined, has a range of angles from minus pi over 2 to pi over 2, which puts you in the right half plane, only accommodates positive X values. If X is negative, then you have to rely on the periodicity of tangents. You have to correct the value returned by our tangent by adding pi. This still doesn't cover X equal to 0. If X is equal to 0, Y is positive, the angle is pi over 2. If X is 0, Y is negative, or minus pi over 2. If the only point I haven't covered is the origin, in which case it doesn't matter what theta is. R is going to be 0. Theta can be assigned any value, and it'll work.
Let's see.
Example here. So xy is equal to minus square root of over 2 and 1/2. Okay. So we want R and theta. R is 1. Okay.
Let's.
So your point is going to be, so X is down here and first I'll draw a unit circle. That's just over audience, so I'll show you the point is right around here. No, wrong.
Okay.
Up here, it's y is positive, only x is negative.
So. Following the directions there, so it would be the inverse of, or actually, no, I got it backwards. Never mind. The inverse of y or x, so 1 over square root of 3.
The inverse tangent plus pi.
Yeah.
Yeah, you have to
And
add
then
pi.
actually plus pi because x is negative as well.
2 pi over 3.
Yeah, not quite. So our tangent would give you this angle right here, which is, minus pi over 6. And then you have to add pi to it, which is,
Should be 2, which from what I'm getting is. Yeah, I'm just making sure this is right, 2.62 radians.
okay,
Is it 5 over 3?
yeah, it is 5 pi over 6.
Oh, okay.
You get minus pi over 6 from inverse tangent, then you add pi to that, and you get
5
pi
pi.
over 6. Okay. Right. Okay. One more. X and Y are equal to -1, so that puts us down here.
We had the add five, wouldn't that be, just like the equivalent to 0? Or no, I'm doing the math wrong.
Oh, here? Oh,
Yeah, oh, up there, I did it wrong. Never
Okay.
mind, that makes sense.
well, someone give me an R.
Where did you?
Yeah.
Mhm.
Okay.
Where did you get them?
Five, 4.
It is, so you get pi, so if you take, if you have tangent of theta is equal to y over x, which is 1. Our tangent of 1 is pi over 4. But then you have to add pi because x is negative. Yes, 5 pi over 4. Any questions about how this conversion was? I mean, a tested, a decimal is fine, because that's what your calculator is gonna give you for a tangent.
Wait, where'd the 4 come from at the bottom? I thought it was over 6.
Oh. The previous example was,
Oh, it's a different example?
yeah, the point's different,
Oh, I was, sorry.
okay. Okay. Yes,
So on the exam, we can use calculator.
yes, you can, yeah. All right, now. Look at polar equations. That's another way of describing curves. You've seen, remember representing curves as y as a function of x. And now we see parametric equations too. And now we have a polar equation. So polar equation is just something in this form. R is given to be some function of theta. Now, if you're given an equation like this, then you can go directly from there to parametric equations. So x would be equal to f of theta cosine theta. Y is equal to f of theta sine theta. So now you have parametric equations for your curve, where the parameter is theta. Okay. I'm going to show you how you can sketch a polar equation. So your polar equation is R is equal to cosine of 2 theta. So let theta run from 0 to 2 pi. So what you can do is, there's two ways you can think about this. You could just use the parametric equations I've written. So in other words, x in this case would be cosine 2 theta cosine theta. Y would be cosine 2 theta sine theta, and just plot x and y values. Or you can stick with polar coordinates, and for each theta, figure out the r value and then you plot that distance. So I'll show you that way to give you an idea of how it works. So, okay. So look at select theta values. So when theta is equal to 0, so cosine 2 theta is going to be 1. So now theta equals 0 is just a positive x-axis. So that's where your point's going to sit at a distance of 1. So this is my point in Cartesian coordinates, 1, 0, corresponding to theta equals 0. Now, if I pick another angle, let's say theta equal to, let's say pi over 6. So cosine of 2 theta, that would be cosine of pi over 3, which is 1/2. Okay. So what that means is I need to locate the ray theta equals pi over 6. And then along that ray, I'm going to go a distance of 1/2. So that put me right around here. So that's how my curve starts out. I go to another angle, pi over 4. What is my r going to be in that case? Yeah, because I have r is cosine of 2 theta, cosine pi over 2, which is 0. So now I'm at the origin. Okay, so this is my point. Okay. Actually, you can write. Okay, so 1/2. Cosine of pi over 6 is square root of 3 over 2. Okay. So here I'm at the origin. And theta is pi over 4. Okay. Now if I go to pi over 2, What's my R gonna be in that case? -1, because I have cosine of 2 theta, cosine of pi, which is -1. So how would I plot that? Well, theta equals pi over 2 is up here. It's the positive y-axis, but I have a negative r. So I'm gonna go 1 unit down the negative negative y-axis. So this is my point. So my curve's gonna go like this now. So that's how a negative r value is taken into account. It's still along this ray corresponding to theta is pi over 2, but I go in the opposite direction starting from the origin. So that's kind of strange, but any questions about how the curve has been plotted so far? What about theta equal pi? Yes, that's right. And you know what? I should not have gone all the way to pi. In between, if I do 3 pi over 4. Yeah, because we're saying cosine of 3 pi over 2, which is 0. So we're back to the origin. And then at theta equals pi, we're out here going a distance of 1. So now it's going to look like that. So, okay. So it's going to keep spiraling around. I'm going to get 4 petals in the end. So that went all the way to 2 pi. Then I end up with that. Oh, wait, I need to finish it.
Is it, what do they call it? Rows of writing, like, there's specific, well,
Okay, but the term comes to mind, but I'm not sure if it's right, so I'm gonna look it up real quick. So I'm cheating here. Oh, okay, it's not a lemon escape. That looks more like an infinity symbol. Okay. I don't know. No, I'm not having you plot a polar curve on the final. Now, doesn't we to be able to go back and forth between polar and Cartesian coordinates for individual points, we all want to be able to do the same for equations. So if you have a Cartesian equation involving x and y, how do you get a polar equation for that, or vice versa? Okay, so suppose we have our polar equation of 3r is equal to 3 sine theta. How do we get a Cartesian equation from that? Okay. Now, one thing that could be helpful is if I take my polar equation, multiply both sides by r. It's not r squared. It's 3r sine theta. So how can we express that in terms of x and y, given a relationship between polar and Cartesian coordinates? How we convert between them.
r squared equal to y.
But what is r squared? How do we write that in terms of x and y also?
X squared plus y squared?
Yeah. X squared plus y squared left side, and yes, then we have 3y on the right side. Yes, so by multiplying both sides by r, that introduces an r squared. And x triple, which is x triple y squared. There's a good way to manipulate polar equations to make that happen. Now, what does this Cartesian equation actually represent? So what I can do is rewrite it by grouping x terms, x terms and y terms together by y squared minus 3y. Okay, but now if I rewrite y squared minus 3y by completing the square, then I'm gonna have y minus 3/2, the whole thing squared, is equal to 9/4. So just by applying the completing a square formula, and then we end up introducing a term of plus 9/4 or minus 9/4 that moves it, that moves the other side. So what curve is described by this equation? The circle. What are center and radius?
And 3/2
What's the center?
and 3/2.
And the radius is 3/2. So, so in general, what happens is when you have r is equal to some constant times sine theta, it's a circle that is perched on top of the x-axis. So it's going to look like this. And then the so whatever constant you have in front of the sine theta, half that value is the radius, and it's also the y coordinate of the center. So r equals a constant times sine theta gives you that, whereas r equal to constant times cosine theta, we'll put the circle over here. Questions about the conversion of that one? Here's another one before we go the other way. R is equal to cosecant of theta. Now, polar coordinates, we like to have things expressed in terms of cosine and sine, not cosecant. So how can we rewrite this in a way that makes it easier to convert? Yeah, so cosecant is 1/sine. Okay, so what can we do to as far as rearranging this to get a easily convertible equation? Yeah, so now we have r sine theta equal to 1. Which in x and y terms converts to. Yeah. So r equal to cosecant theta is just a horizontal line. Similarly, if I had r equal to secant theta, that would give me a vertical line. So the other way, start with an equation in Cartesian coordinates and convert to polar. The 2cx, c is some constant.
Squared. Do you see our cosine?
Yeah. Okay. And then if we divide both sides by r. Now we have a, polar equation. The normal standard form of polar equation is r is equal to some function of theta. What kind of curve is this? Somewhat similar to this example.
On the horizontal axis.
Yeah. It's a circle. So in this case, we had 3 sine theta, and the radius turned out to be half of that, and the center turned out to be 0 and 3/2. So if you extrapolate from that to this case, e minus with the x term instead of the y term, possible to see what these examples have in common to figure out what the center and radius of this circle would be.
Center 2c/2 0.
Yeah. So x for the c, yeah, half of the constant.
So just.
Yep. Yeah, the radius is going to be, again, half a constant. Questions about these conversions? Previously, we saw how to get the tangent to a parametric curve. Now we can specialize that to the polar case, figure out how to get tangent to polar curves. Now, so if this is your polar equation, r is f of theta, that I wrote down earlier, x is, the x is r cosine theta. Y is r sine theta, where you would fill in f of theta for r. So these are parametric equations of your curve. Now, we saw before that it tangent parametric curve, a slope, the tangent line is dy d theta, or theta is whatever parameter you have, over dx d theta. And since we have these formulas here for x and y, we can take the derivatives of these. And what do we need to use to take the derivative of these with respect to theta? Yeah, I gotta use a product rule. So we end up with the y, f prime of theta sine theta plus f of theta cosine theta up top. And then down below we have f prime of theta cosine theta minus f of theta sine theta. So that's how you get the slope of the tangent to a polar curve. Now, of particular interest are points where the tangent line is horizontal. Then you might have a max or min of a curve. Also where the tangent is vertical, so dy dx is goes off to infinity in that case. Okay, so right. Here's some special cases of interest. A horizontal tangent. Well, so normally that's when dy dx is equal to 0. But in terms of the derivatives with respect to theta, that means we need dy d theta zero, but dx d theta must be non-zero because otherwise the whole fraction is undefined. So if you're asked, where does this polar curve have a horizontal tangent? You look at dy d theta of the numerator here, see where it's equal to 0, but make sure that whatever you get, that the denominator is non-zero at those theta values or we don't count. Similarly, vertical tangents. You want slope going to infinity. So that's where dx d theta is 0, but dy d theta must be non-zero. Because if you have a non-zero number over 0, that's something that's going to infinity. So it's the opposite situation of horizontal. And finally, at r equals 0, which is referred to as the pole. So f of theta is 0. So that means that these terms are going to disappear. And then in the other term, f prime of theta is going to cancel out. So in that case, dy dx is equal to tangent of theta. Dy dx tangent of theta, provided that f prime is non-zero, because that prime of theta equals 0, you're not able to cancel them out. Okay. Let's try this out on an example. Okay, so our polar equation r is equal to sine theta. We'll only consider theta being 0 and pi. Where's the tangent line horizontal? Horizontal or vertical? Okay. So we look at a formula for dy dx. So our general formula is R prime sine theta plus R cosine divided by R prime cosine minus R sine. Okay, so we go ahead and fill in the fact that R in this case is equal to sine theta. Then what are we gonna get? Starting with the numerator.
Cosine theta sine theta plus cosine squared.
Almost,
Oh, plus sine theta.
yeah, so you get two sine theta, cosine theta, okay, up top, and then down below.
Doubling.
Yeah, for both of them, sine two theta up top,
um,
theta down below. Okay. So to see where the tangent might be horizontal or vertical, let's look at where the numerator denominator are equal to 0. And we only care about theta value between 0 and pi. So this is equal to 0 for which theta values? Uh-huh. One more.
Right.
Yeah, pi.
Yeah.
Okay. All right. Okay, so, and what about cosine? Where does that equal to 0? Keep in mind it's cosine of 2 theta. So this 0 and
1/4.
one more. Got it, 0 here. Let's the angle down here.
That's not right.
Wait,
But it's cosine of 2 theta. Is that what you had? It is 3 pi/4. You see why? Yeah, because this angle works down here, it crosses like 3 pi/2. So you want 2 theta to be 3 pi/2. Therefore, theta is 3 pi/4. Okay, now. Okay, so with that in mind. Okay. Okay, so a tangent is. Tangent line. Is. Okay, so where's, do we have a horizontal tangent? So dy d theta must be zero as long as dx d theta at that same theta value is non-zero. So basically, this is what we collected here.
Yeah, it's just the point.
Yeah, so 0, pi over 2, and pi for horizontal. Pi over 4, 3 pi over 4 vertical. So at least they didn't have any zeros in common. Okay. Now, what you could do though is substitute those beta values into your polar equation. Okay, so. All right. Okay, 0, pi over 2, and pi for horizontal tangent, and then pi over 4 and 3 pi over 4 for vertical tangent, because I want to see where in the XY plane, like what are X and Y values, where these horizontal or vertical tangents occur. So you can substitute these into your polar equation, R equals sine theta, to get the R values. So you're going to get 0, 0, 1, square root 2 over 2, square root 2 over 2. And then you can map those to X and Y based on X is R cosine theta and Y is R sine theta. Now where R is 0, certainly X, Y is 0, it's the origin. Okay. And then when at pi over 2, you have X is cosine theta, which is 0, and Y is sine pi over 2, which is 1. Okay, so then if I draw that later. Okay, here we have cosine and sine of pi over 4 is square root of 2 over 2. So we end up having 1/2 and 1/2. In that case, and then for 3 pi over 4, you have cosine of 3 pi over 4 is negative minus square root of 2 over 2. So you end up with minus 1/2 and 1/2. Notice all my y values are positive. So I mentioned previously that if you have r equals a constant times sine theta, it's a circle that sits on top of the x-axis. Okay, so at 0, 0, we have a horizontal tangent. And also at x is 0, y equals 1, also a horizontal tangent. But then at x is equal to plus or minus 1/2, then y equals 1/2, you have a vertical tangent. So these are your tangents, horizontal, vertical, and since this is a circle, that's actually what we would expect. Okay, so horizontal to top and bottom, vertical tangents to the left, far left and right.
It's number that's like halfway next to the bottom right now.
Sorry, what?
Next to the very tip of the bottom.
Oh, this?
It's a number
No,
now. Okay.
that's much. So here we have the origin, and 1/2, 1/2. If there's a circle of radius 1/2. Center. X is 0, Y is 1/2. Okay, So any questions about finding horizontal and vertical tangents? I know. Whoops. I just wrote last example, too torturous for me. Well, also, it corresponds to something from the calculus textbook that we used to use back then, so I don't have all the information in front of me. But it's another exercise in just finding polar tangents, but, actually, if I look at the final, um, and relevant questions here. Okay, it's arc length, do it tomorrow. Okay, good. Okay, yeah, so one of the problems in practice final is determine values of theta where the curve has horizontal tangents. Actually, that's the only polar tangent related question. There's converting between polar and Cartesian, and then arc length of a polar curve, but that's something I'll cover on Wednesday. So that's the extent of your required polar knowledge. And there's 20 questions, I can't ask very many questions about any one topic. Okay. All right. Yeah. We're done. Well, I'm gonna stick around in case anybody has questions, but yeah.